This is not the video I intended to make. And it all started with such good intentions. All I wanted to do was a few small side projects. And maybe make a mini video about the process. But what is that saying about planning and laughing? But I'm getting ahead of myself. Now, it has been suggested once or twice that I should be using something a little more secure than MDF and blue painter's tape if I want to achieve greater precision. So I thought I'd start the new year off right and build a new tooling plate for the CNC. And if you're wondering, isn't that a tooling plate already on the machine? Yeah, you're right. And it is nice and thick, but the threads are pretty rough and worn out. So the plan was to turn this existing tooling plate into a bunch of super glue fixturing plates. No, I'm not getting rid of the super glue. I'm just upgrading. So the goal was to build a nice, shiny, and new base plate that would utilize 1/4-inch hardware for my lightweight router. And this would be a 2-stage design to make it simpler to manufacture, and the raised section would be just within the travel of my machine, allowing me to neatly level the base plate once it was installed. And this was all actually going pretty great. I roughed out the general shape and ran some finishing passes to clean them up. And then came time to drill and tap literally hundreds of holes. Thank God for thread milling. These other holes are for dowel pins to aid in fixturing, and here's where things didn't come together as nicely as I'd like. The holes were tapering slightly, and I tried adjusting my formula, and I took lighter cuts and lots of spring passes, but I think the rigidity of this tool is just insufficient, and this is where a reamer would really be the right tool for the job, but my machine would definitely not handle reaming. In addition, the fit on these dowel pins is not perfectly consistent. Depending on the location, some have ended up on the tighter end, and some have ended up kind of loose. So I think the dowel pin idea is kind of a bust for now. In any case, the chamfering went smoothly and this first tooling plate was done. So I quickly started on the second one, and it was pretty much exactly the same as the first. And I was 90% of the way there. And then, disaster struck. Mid-cut, the spindle shut down, and an error message began flashing on the VFD. And after a bunch of troubleshooting, I determined that the VFD was officially dead. And this was made especially apparent when I realized it was sending straight 110 volts down one of the motor legs, even in its error state. Scary. So I did have a cheap replacement VFD laying around, and luckily the spindle still seemed fine. So it was time to open up the control panel and do a little surgery. But before I do that, I'd like to talk about black holes. And I'm not talking about those interstellar masses in the center of our galaxy. No, I'm talking about black holes in the shop. And I think we all have them. Our secret shames. Maybe it's that corner that you can never quite keep organized. Or maybe it's a kludged together project that works just enough, yet always seems to cause problems whenever you try and use it. So you develop workarounds, you adapt, but you never fix the problem. And there's a very good reason for this. These problems aren't sexy, and more importantly, they're a trap. So my usual strategy for dealing with these black holes is to just ignore them. If you don't get too close, it can't suck you in, right? But sometimes you have no choice, and your long-running hack job finally fails. And generally, you can deal with this in 2 ways. You can do a quick band-aid job, patch it up, and try and forget about it until the next time it catches you. Or you can let the black hole draw you in, until you're in way too deep and there's no escape but to go through the other side. So I obviously decided to go with option number 1 and jammed my new VFD into the same old control box. I wired it up and finished machining up the second base plate. Cool, video over, is what I would have said if I'd left it at that. And I really tried to do just that. I really, really tried. Yeah, I'm just sick of this whole CNC control situation.
This is war with the enemy. Think that it was meant to be. Living in a time where disease is on every screen. I won't let them fester me. I know most are festering. Negativity is a plague for the mentally weak. No mercy, all I got is worth.
I have lived with this hacked together box of wiring and components long enough, and I've had more than a few gremlins, and I can't help but think that this whole situation right here might just have something to do with it. I think it's time to do this right and build a proper panel for the CNC. And frankly, this is all pretty good practice, because I'm going to have to do this again with Marge 2.0. And since I was redoing the panel, I figured maybe this was a good opportunity to reevaluate the controller I've been using up to this point. So this is the DDCS. It's a standalone controller that I bought from Amazon, and it works fine for basic operations. But I'm doing more advanced work with the CNC, and I'd like some features that the DDCS doesn't easily support. You know, things like 3D probing routines. Things I didn't know I wanted or needed when I first got started on the CNC. So the controller is being replaced with one that supports these more advanced functions. And while I'm at it, I think it's time to maybe replace the limit switches. But instead of just replacing them, why not upgrade to something better? Inductive proximity switches. These have no moving parts, so this should increase reliability. And since we're now replacing components on the CNC itself, I think we should probably rewire it, and I'll explain the reasons for that shortly. And since we have the controller to support it now, we might as well add that 3D touch probe and a tool setter. For now, I'm drawing the line at a mist coolant system, but I'm going to add all the provisions to make that pretty much plug and play in the future. And now that I think about it, having the controller right next to my grinder has meant that I'm terrified of using the grinder. So that means putting all the controls on the opposite side, which means these two cabinets have to go, which means the door needs to be reversed, and we need to make provisions for mounting a monitor and keyboard. And we might as well add a few physical buttons as well, because we've gone this far, and buttons make you feel like a real machinist. So yeah, hopefully now you can see why I call it a black hole. So with a very general sort of plan in place, let's take a closer look at what goes into the controller. And I'm just going to get this out of the way now. I am not an electrical engineer, and the following is just a record of my design and thought process. Please do your own research and don't mess with mains voltage without proper precautions. And should you want to brush up on your electrical fundamentals, or maybe just learn a little bit more about black holes, you know, the galactic kind this time, then I highly recommend you check out this video's sponsor, Brilliant. Brilliant helps you get smarter every day with thousands of interactive lessons in math, science, programming, data analysis, and AI. Now, I've never been the best when it comes to memorizing facts and figures, and that's why Brilliant's app has been a great fit for me. Brilliant builds critical thinking through problem solving, so you're building actual knowledge on a subject, knowledge that you can then apply to the real world. Brilliant's interactive problem-solving method helps you become a better thinker, which comes in handy when it comes to troubleshooting your own projects. I've been using Brilliant science courses to catch up on my electrical knowledge, and the interactive nature of these courses is perfect for learning the fundamentals of how circuits work. Like me, you might not be an actual electrical engineer, but you can learn to think like one with Brilliant. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/cinemamechanics, or scan the QR code on screen, or click the link in the description. You'll also get 20% off a premium annual subscription. So thanks Brilliant for sponsoring this video, and now back to it. So first off, there are a variety of power supplies that are needed to provide the various voltages our components operate at. And the biggest one provides 40 volts to the 4 stepper drivers, which control the 3 main axes, plus a 4th for a rotary axis. The smaller power supplies provide the various voltages needed for the controller and all the other accessories. And most of the rest of the panel is dedicated to power distribution in the form of various terminal blocks. Next, we have a few relays to control the coolant system. And finally, we need the CNC controller itself. And you might notice one conspicuous absence in the new layout. Yeah, where's the VFD? Well, it's my understanding that best practice actually dictates that the VFD should not be in the main control box. And this is because the VFD is a significant source of EMI, noise, interference, whatever you want to call it. And since we're trying to do this right, we're going to follow that advice and mount it as far as practical from the control panel. The metal enclosure will act as a Faraday cage and help shield the components from external EMI, but internal sources will just bounce around inside the enclosure, so we want to keep the noise produced inside to a minimum. So with a general idea of what's needed, now I just need a big box to contain it all. I chose to do a rough layout in CAD since many manufacturers provide models of their components, and I really wasn't sure what size box I'd need. I promise you, no matter how big you think your box is, it never seems to be enough once you actually start to stuff it with components and wiring. As I mentioned, I also need a bunch of terminal blocks and other bits and bobs to hook everything together. So the parts were on their way, and I need to scavenge the rest from the existing control box. But I had one final job for the CNC before ripping its heart out. And that's the connector panel for the new enclosure. I had some mystery sheet metal laying around that was already powder coated, so I cut off a section and glued it down. And this went pretty well, despite the fact that this aluminum was super gummy and totally broke an end mill. I think it didn't help, I only have up-cutting end mills, and for sheet metal I'm pretty sure you're supposed to use down-cutting. In any case, some WD-40 solved the problem, and then I did some quick engraving to make the labeling look super slick. Not bad for my first sheet metal part. So now might be a good time to sit down and really plan out all the connections. And I broke this down by voltages. So first off, listing all the components powered by mains voltage. Then I went through each of the power supplies and listed all the components that would be connected to them. And this included all the components connected via the control panel. And this should give you a pretty good idea of how many terminal connections you need for each of the power supplies. And next I went through the controller I/O and listed all the signal connections that I was planning on using, and what signals were going to the connector panel, and which signals were going to components within the enclosure. And finally I broke down the ground connections, which I'll get into a bit more shortly. Once everything's listed, it's a really good idea to draw a diagram of all your connections, and you can do this however you like, but I chose to break it down by voltages once again, and then draw out the signal I/O separately. And yeah, I really did just draw all this by hand at first. I think it's a lot faster than designing it up in CAD. And once everything arrived, I spent way too long trying to figure out a good layout for all the components. Yes, I had planned this in CAD, but it's just different when you actually have all the components in front of you. Now we have a bunch of goals we're trying to accomplish as far as component placement is concerned. First off, we're trying to keep all of our wiring as clean as possible. So that means we definitely don't want the high voltage AC lines running alongside low voltage signal lines. We want to keep the various supply voltages organized, isolated, and cleanly routed to their destinations. And we want signal lines to be as short as possible, and again, as separated as possible from the higher voltage lines. We also want to consider cooling. We need enough space around each component to ensure proper airflow. And ideally, we want the heat generating components down low so the heat rises away. And we'll use fans in a push-pull configuration, drawing cool air in at the bottom of the panel and evacuating it out the top. What I'm trying to say is that it really pays to take the time to think this out carefully and experiment with different layouts until you have something that works for your needs. And despite a ton of decision paralysis, I finally settled on a layout. Next, I marked out the mounting positions for the key components and for the rail. I want to have all the messy stuff finished before I start installing the delicate electronics, so I chopped out the bottom of the box where the connector panel would fit, and I used a hole saw to cut out the 2 fan holes, which wasn't fun with a cheap off-center hole saw. I tried my best to drill out any of the other mounting holes I could think of on the exterior of the enclosure. Then it was time to mark and drill out the back plate, once again double checking the positions of all the components for clearance. And once satisfied, I drilled out and tapped all the required mounting holes. And with hopefully all of the dirty work out of the way, it was time to start installing the first of my components and start the long process of wiring everything up. Now, I'll be the first to admit, it's pretty easy to get overwhelmed when you first start wiring up components. What looks simple on paper feels more complicated when you actually start laying out the wires. And what looks complicated on paper Looks like a tangled Medusa mass in real life. So it's best to take it in small steps. I started with the mains voltages, for example, since it's pretty simple compared to the low voltage distribution. Plus all the wiring is pretty isolated from the rest of the panel. So power comes in from a fused inlet on the connector panel and goes immediately into an EMI filter to clean it up. And from there it runs up the left side of the panel and into the AC mains distro portion here at the top. Power first flows through this relay, and then into the terminal block. And I have bus bars for line and neutral, splitting these lines to feed the 4 power supplies. Nothing is piggybacked, every component has a dedicated connection on a bus bar. And while we're here, we'll run the grounds for these mains powered components. Each supply is directly connected to the ground bus. Again, no piggybacking allowed. The ground bus is connected to the ground pin on the power inlet, and the chassis is bonded to ground here as well. And this probably makes for a good time to talk about the grounding strategy in general. So basically what we're going for is a star ground, where all the grounds go directly to one place. And this reduces the possibility of a ground loop, and is again considered best practice. And this means that all the grounded components get a dedicated connection, or bond, to ground. In addition, we'll be using shielded cabling for all the connections outside of the panel. Shielding is basically a jacket of braided wire or foil, or both, which wraps around the length of the cable. The shield helps the cable reject EMI and provides a more stable signal to or from the controller. They are often confused, but the shield is not the same thing as ground. However, every one of these shields needs to be drained or connected back to ground. And there is more than a little debate about whether the shield should be connected to ground at both ends of the cable or not. And I'm choosing to only bond the shield drain to ground on the panel side of the cable, called a telescoping shield, which some might call the old school way of doing it. And this has worked for me in the past, so I'm sticking with it. But feel free to debate the pros and cons in the comments. The CNC router chassis also has to be grounded, but we're going to do that through the spindle later on in the build. Now, I don't want to get too in the weeds in this whole grounding discussion, but there is one last controversial topic we need to cover. And that's whether or not to connect the negative terminal of the power supplies to the ground bus. In many DC power supplies, the negative terminal is not connected to ground, and nomenclature gets really confusing here, because a lot of circuit boards refer to DC negative as ground, even though it might not actually be connected to your physical ground. The negative terminal is really essentially just the return path for the power supply's positive output, so many designers choose to bond this terminal to ground. And there are many arguments for choosing to do this. Arguments that are beyond the scope of this video. In any case, I decided to go with option 2 and have maintained the isolation between ground and DC negative. So from now on, I'll refer to this negative terminal as signal ground, as opposed to earth ground, which is what ultimately connects to our outlet at the wall. And to be honest again, this is just how I've done it in the past and it's worked. But I am looking forward to hearing all the reasons for why I might have done this wrong. Similarly, there are a lot of arguments about whether or not you should connect the signal drains to earth ground or signal ground, and I chose earth ground. But you'll find out when you do your own research that there are a lot of very strong opinions on the subject, so you'll have to make your own decisions. Okay, I know that was a lot, and I know it's kind of a pain to wrap your head around proper grounding. But if you're going to play in this sandbox, you kind of have to do your best to learn it. So to take my mind off all this grounding mayhem, I decided to start soldering up my connector panel. And there was a fair amount of soldering required, so I just kind of did it a section at a time. And I left the wire pigtails over long so that I could cut them to length once everything was routed properly. And then it was time to work on the power distro for all the various DC voltages. I started with the 24 volt portion, and after soldering up the relevant panel connectors, routed those wires back to the 24 volt terminal strips and relays, and cut them to length. And these particular terminals don't require any kind of ferrule or other connector, so they're pretty convenient. And again, no connection is ever piggybacked, and we have a dedicated terminal for every single connection. The 40 volt system came next, and this is relatively simple since it only powers the 4 stepper drivers. The power supply has a 3-position terminal built in, so I wired 2 of the drivers directly to that. The other 2 were connected via these terminal strips, and since I was working on the stepper drivers already, I soldered up the motor output connectors and routed all the wires to their respective drivers. And now for a quick tangent. I have visions of this beautiful organized workspace while I tackle projects like this. Visions of creators in immaculate workspaces cleanly assembling components just feels so satisfying. And this is what my workspace looks like when I work on projects like this. So yeah, YouTube is a rotten liar. Okay, enough stalling. It's finally time to install the 5V and 12V system, as well as the controller I/O. And this is a big job. There are limit switches, probe and tool setter inputs, relay outputs, digital I/O, control signals like run and hold, and the all-important emergency stop. And some of these connections require additional 5V power, like the probe and induction switches. So yeah, you just kinda need to take it one connection at a time, and do your best to stay organized. And all the signal lines coming into and out of the control board are going through ferrites. And again, this is an effort to protect them from EMI. We could also use shielding for this internal cabling, but then we'd need to add a heck of a lot more drain connections. So ferrites are a good way to protect them instead. A 3D printed guide helps keep all the connections neat and organized. And along that same vein, this bracket provides for a variety of attachment points for organizing the cable routing. And ferrites were also added to all the wiring at the connector panel, for good measure. And remember how I said that signal ground is separated from earth ground? Well, these terminals provide a bunch of extra connections for this signal ground, for wiring up the stepper drivers to the controller. And finally, the stepper drivers get their signal wires connected up to the controller. And now that we've soldered up all the connectors for the panel, each signal drain is connected to the earth ground terminals nearby. And that more or less covers it for all the I/O. And last is a shielded Cat5 cable that connects the controller to the bulkhead connector. Using Ethernet to communicate with the controller is preferable to USB due to a much more stable connection and increased EMI resistance. Now it should go without saying, but you should be checking your work constantly throughout the wiring process, double checking every single connection, using a meter to make sure there's continuity where there should be, and no continuity where there shouldn't be. Double check that you haven't crossed signal wires or miswired any of the connectors. I, for example, miswired the stepper drivers and had to redo them. So now it's time to install the panel into place on the left side of the enclosure. And next I got to work pulling the CNC machine out of the cabinet and giving everything a good cleaning. And then it was time to strip off all the old cables, cable chains, and limit switches. None of this old cable is shielded, so now's the time to replace it. And the new limit switches need mounting, so I quickly fabbed up a few mounts out of some scraps and corner brackets. These don't need to be fancy. The switch makes no physical contact, but they should be sturdy enough to keep it held firmly in place. The new motor and spindle cables are double shielded and wire chain rated, so they're designed to survive repeated flexing. And double shielding just means it has both a braided and a foil shield. And more is better, right? So there are a few ways to deal with terminating the shield. One is to couple it to the connector housing itself. The other is to pass the drain through a spare pin in the connector, and then attach that drain to ground within the enclosure. And I chose this route because it requires less hardware. So my 4-wire motors are connected with a 5-pin connector. And as mentioned before, the other end of the shield remains unterminated. The rest of the cabling was installed with the machine back in the enclosure, allowing each cable to be routed and cut to length one by one to minimize waste. And when I originally built this CNC enclosure, I had made a sub-panel with connectors inside the enclosure. This time around, I opted to directly pass the cabling through the enclosure and use 3D printed grommets to seal the holes. Removing these extra connections just keeps things simpler and more reliable. The air lines and spindle cooling lines were also routed through the cable chains at this time. Next, I needed a way to mount the touchscreen, the keyboard, and the PC to the enclosure, and this gas spring monitor mount should serve the purpose for now. A keyboard bracket purchased on Amazon gives me a nice self-contained workstation with a good amount of adjustability. The PC itself is a tiny micro that's mounted underneath the keyboard shelf on some 3D printed brackets. And this setup mostly works, but if I'm being honest, I'd like a little more stability, so I'll probably replace the arm with something heavier duty in the near future. Next, I modeled and printed an enclosure to house the physical buttons that will help control the CNC. I have a start button, feed hold, and an e-stop, plus 2 power buttons, one for the control panel and the other for the VFD. A 24-volt power supply in this enclosure provides power for the panel and VFD relays, and powers the cabinet lighting and ventilation. And yeah, you could do all this a bunch of ways. This is just how I did it. So with the buttons all wired up, I could finally power up the panel and start an extensive round of testing. I started by checking the easy stuff, the button connections and e-stop functionality. We kinda need that in case something goes wrong. Then the relay outputs for mist and air. Next came checking each limit switch and adjusting each one to trigger at the end of travel. I then proceeded to test each motor, confirming correct operation and direction. Next, I configured and checked the homing sequence, and set the soft limits to correspond with my machine's travel. Finally, I tested the probe inputs and tool setter inputs to confirm that these functions all worked correctly. And the tool setter has an over travel switch wired in series with the e-stop to halt the machine in case of probing error. And by the way, every single input to the controller is wired and configured as normally closed, and this helps prevent false triggers due to EMI, and provides a bonus protection from wires being disconnected. So with all the motion and limits properly configured and tested, it was time to tackle the VFD and spindle. And the VFD needs a little bit of distro and a place to house the main power relay, so I picked up a small plastic enclosure to house all that. And this will contain a few terminal blocks to distribute mains power to the VFD, as well as an additional output for a spindle cooling pump. And this is all fed through a relay in the same manner as in the main control panel. And finally, we have a ground bus, which will not only ground the VFD and the pump, but also the CNC machine itself through the ground wire running to the spindle. And as always, we need to connect the drain for the spindle shield. The VFD and distro panel were mounted up on the wall, and I would have liked to mount it a bit further away, but this was the most practical location that still allowed for some distance between the VFD and the rest of the electronics. The VFD and pump were wired up to the distro box, and the spindle was wired to the VFD, and finally the control signals from the control panel were routed and wired into the VFD. And finally I could start testing the spindle, and here's where things went horribly wrong. Analog output. Something wasn't quite right. The 0 to 10 volt output would drop. The shield connection. This was a stupid project. Why not try connecting the shield to ground at both ends of the cable? But maybe this cable is just special. Okay, working motion system, check. Working spindle, check. Final step is to ensure proper grounding of the chassis. So the spindle is grounded at the VFD panel, but using a multimeter and testing the resistance of the frame at various points from the spindle, we can pretty easily see that the frame doesn't conduct particularly well, probably due to all the bearings and such. And this means that large parts of the chassis are not well grounded. So we want to lower this resistance and provide a clean path to ground by bonding the various parts of the chassis back to the spindle using ground straps, which is usually made of flat braid for reasons. Did I say that was the final step? No, there are a few more things, like wiring up the cabinet LEDs. Oh, and labeling everything. Transparent heat shrink over adhesive labels is a great solution for labeling thicker cable. And after all that, I'm essentially exactly where I started over a month ago, with a working CNC. In fact, I'm not even there yet, since I still have to calibrate the machine and configure the post-processor, and do a whole bunch of other testing. And I need to install those base plates. You probably forgot about those. And I need to test and configure the fourth axis, and I'm working on a solution for a pendant as well. So much more to do, but here's the setup as it currently stands, and I, for one, am pretty pleased with the results. The new CNC. Same as the old CNC, but better? Oh, and one last thing. Viewer Tim Fans recently contacted me and wanted to contribute to the channel, and very generously sent me a Venmo. So if you want to be like Tim, I've made it easy by starting a Patreon and YouTube channel membership. Supporters and channel members will get access to videos early, as well as hopefully some other great perks in the future. So please sign up if you want to support the channel and help me continue to make great content. Thanks so much for watching, and stay tuned for the next one.